wait there. Okay, so let's start with this topic of power amplifiers for today. So feel free to stop me at any time, right? This recording can include all your questions also if you want. So I think I'll specifically point out that primarily it's going to be CMOS power amplifiers because you will find that the design of CMOS power amplifiers is slightly different from that of other power amplifiers, primarily due to technological limitations rather than anything else. Okay, so I think let's see. We'll first, what we'll do, the way I'll do this class is to start off from scratch, right? We don't know anything, right? I'm going to ask you guys questions and you come up with what we can do, right? Then what we'll do, we'll look at different variants of what are possible from the, from general amplifier side. So the first thing, right? Before we go there, we need to understand, what power amplifiers do, right? So the first question is, uh, does any of you know what a power amplifier is and what it does? That's the first question. So, well, so normally the power amplifier is right at the end of the transmit chain, okay, and it is used to drive the antenna. For an RF power amplifier, this is the kind of application you're looking at, okay. Obviously, there are also other power amplifiers. Example, you can have a power amplifier for audio systems, right? They will of course look different, right? There is some basic power amplifier theory that we need to do. We'll try to look at it briefly, a little bit later in today's class. But before that, let's specifically understand what is required of the RF power amplifier. So the first thing is that I'll show it like this. So this is of course the diplexer or duplexer. Okay, diplexer is normally a duplexer that operates with different TX RX frequencies. Okay, if the TX and RX frequency are the same, then it's officially a duplexer. Okay, people were a little bit more loose with language till a few years ago. Okay, so if you have FDD systems, you would need a filter that is called a diplexer. If you had a TDD system, you'd need a switch, okay, that would switch the antenna between the TX and RX. I'll call this FD, standing for full duplex. Okay, if you have full duplex systems, then you would need a duplexer. Okay, this of course goes into the RX. Okay, this is the RX. Now we are specifically interested in this particular block. Okay, so the first question, what does the power amplifier do and why do you need it? Okay, so obviously to start with, the remote receiver that you are transmitting to is very far away. So based on the range of the system, you'll come up with a specification for the output power that you need. That's the first thing, right? The output tower, so the range comes from the application. If you want wireless LAN, people get together and decide that wireless LAN standard needs to have a range of, let's say, 100 meters. Okay, if you're looking at cellular, 100 meters is just not good enough, right? You'll just need too many base stations. It's not economically viable. Okay, it's also not good enough. So you want to have at least let's say a kilometer, couple of kilometers type of range before you want to, it'll be viable for cellular. Okay, if it is Bluetooth, it may be much smaller. It may be like 20-30 meters and so on. Okay, so the application decides the range of the transmitter, of the transceiver. Okay, the distance, the range will automatically decide the amount of power that you need to put out. Okay, the reason is very simple. Remember the link budget that you folks have seen before. You have a certain sensitivity that you need to achieve at the remote receiver, correct? How do you get that sensitivity?
Like we have that SNR floor and other minimum power.
So the first thing is the antenna itself has a noise floor of minus 174 dBm per hertz, right? Above that you add the SNR required. Above that you basically add the 10 log of the bandwidth of the signal, correct? And finally you add the noise figure that the receiver is going to add. Remember, that's your link budget. That is how you get the sensitivity, right? Now depending on the bandwidth of the system, right, you can achieve a certain amount of sensitivity. If you look at like various CMOS types of receivers, okay, the noise figure can be anywhere from the range of a few dB to maybe like let's say 2-3 dB to maybe 7-8-10 dB. Okay, this is the range of noise figures that is already known, right? That's a technological limitation. Okay, so once the bandwidth of the signal is set by the application. Once you do this, the receive sensitivity is known. What is the best possible receive sensitivity that you can achieve, right? That is known. Now you work backwards from figuring out what is the approximate attenuation you get over that range. Okay, you can automatically set an a total transmit power that you need to achieve. Okay, the maximum transmit power that you need to put out will happen when you have the transmitter and receiver are at two opposite ends of the cell. Okay, maximum distance between them, and so therefore the receiver receives minimum power. Okay, so that means at that point your transmitter needs to put out so much power. Okay, that of course depends on the range now. Okay, if you look at cellular systems till 4G, you are putting out about a watt of power. Okay, I'll say approximately 1 watt because it can change a little bit here and there. Okay, GSM for example earlier used to put out a little bit more. Okay, maybe close to 3 or 4 watts. Okay, if you look at Wi-Fi, okay, it's about a few hundred milliwatts, hundreds of milliwatts. Okay, the range is slightly smaller. If you look at Bluetooth, it's a few milliwatts. You can see it's directly tied to the range of the system. Okay, now depending on the application, right, of course the output power of the power amplifier changes. Okay, it turns out that assume that either the duplexer or the switch or the diplexer, whatever you're using, is matched. Okay, and it has very low insertion loss. You understand what I mean by very low insertion loss? From this port to this port, it has very low insertion loss. Normally, it will have some insertion loss, sub 1 dB normally. Okay, if that is the case, you need to add on that insertion loss to the spec on the PA. Okay, if the switch has a 3 dB loss, you'll have to put out twice the power from the PA, clearly. Okay, when you work out the system link budget, you'll have to take into account all of these things. Now, let us say you work that out. Okay, clearly these systems are all RF systems. The diplexer, the antenna, they are all matched to 50 ohms. Okay, now it's clear that the power amplifier needs to drive 50 ohms. So from a circuit's point of view, we can now say that the model of the PA that we are going to have, right, is that it is going to drive 50 ohms. Okay, it is probably going to have a power supply, going to have a ground. Let us say that is some VDD and ground. Okay, it is going to have 0 and VDD. The input comes from the transmitter. It could come from another amplifier which is able to drive the input impedance of the PA. Okay, it could come from something else, from the mixer, for example. If you have enough swing from the mixer, you can run it with the mixer, right? Excellent. Now, I want to put out a certain amount of power onto the 50 ohm load, correct? What is that limited by? I want to keep increasing this power. What is the limitation? Huh? Okay, why is the swing limited?
Because swing can make the transistor settle to non-linear.
It can make the transistor settle to?
Non-linear.
Okay. What is this nonlinear region that you speak of?
Like when we do the small signal analysis.
But so one thing you have to remember, when the PA is putting out so much power, it is no longer small signal, right? If the PA is putting out anywhere, more than a few milliwatts of power, it is no longer small signal. That's what you'll find. We are going to do the calculations now. We'll take an example and do the calculations. This cannot be called small signal by any means. Okay, that's the first thing you have to learn. It's the power supply value. It's the value of VDD. Okay, the value of VDD will fundamentally limit. Okay, because if there is any limitation in terms of voltage on the circuit, it is a power supply. Correct? So in some sense, you will find that in almost all cases, it is a power supply that will limit the maximum output power that you can put out. Of course, there are other things also. We'll look at every component of this and figure out what to do. Okay? Very good. Now, before we go ahead with the rest of the stuff, let us say of course, the power amplifier also requires gain, correct? So you want to put out power, but the number one thing is output power, but number two thing is also gain. Okay? The circuit should also put out gain for various reasons. So obviously the PA is going to be somewhat nonlinear. Okay? Now, if the PA does not have a lot of gain, what will happen is even the previous circuits will also be in the nonlinear regions. That is not necessarily the best, right? So you would prefer the PA to have some gain. Okay, imagine the PA is putting out volts of swing, right? You would prefer that the PA has a gain of 10 or 20, so that at least you are only at hundreds of millivolt swing coming out of the previous circuit, right? Does that make sense? Okay, so we are going to try to build a PA which at least has some gain. Okay, it is also possible to build a PA with gain of 1, but we don't want to do that. Okay, what kind of circuit would you choose? That's the first thing. Now we are going to implement this using MOSFETs. What kind of circuit would you choose and why? Let us look at the gain itself. What are the circuits that you know? Common source amplifier, common gate amplifier, common drain amplifier. Those are the three common things. Which of these gives you gain? Common source and common gate give you gain, right? But common source is better because the input impedance is, I'll put it in a different way. Of course, it's capacitive, right? So you don't put in real power into it. So that is one advantage. The other advantage is, of course, capacitive loads can be easily driven by other CMOS amplifiers. That also you know, right? It is harder to drive a resistive load compared to a capacitive load. Most importantly, it can give you maximum amount of gain, right, compared to the other two structures. So we will choose the common source amplifier. So let us start with that. Would you choose NMOS or PMOS? NMOS, because it gives you more gain than PMOS. Okay, so we're going to start with that. Now, this is the common source amplifier, correct? Okay. Do you know something which gives you even more gain than a common source amplifier? Cascode. Really?
We use cascode, we are limited.
Why does a cascode? You're limited by?
Your swing is limited compared to not using a cascode.
Not using a cascode, of course. You know that cascode gives you swing limitation. This is exactly the minute the load is 50 ohms, right? So you would have seen various structures, okay? So I think the ones that you are thinking of giving you more gain are the case where you have something like this, correct? If you have a case like this, okay, then cascode, it looks like cascode might give you more gain, but remember that you always have the 50 ohm load. Okay, so now I'm going to add the blocking capacitor to make sure that the bias is not affected by adding the 50 ohm load. Will a cascode give you more gain than a regular common source? Most probably not. Okay, so to start with, it looks like there is no reason to go to a cascode, but as you will see in a few moments, right, you will almost definitely need a cascode if you're building in CMOS. Okay, so let us assume that you don't need it, okay, and we'll see why you need it later. It's a very simple reason. Okay, so let's assume you don't need it because it's simpler to work with. So do you need anything else? Huh? Output matching. So one thing which you might need, I say might, but you will usually need it. Note that the S22 at the load, this is an unmatched power amplifier, correct? let us start with this anyways, even though it is unmatched. Okay, so clearly S22 is not equal to 0, it's not matched. Okay, but we will start with this anyways. Okay, we'll come back to figure out why or how we'll match this. Okay, how do you build a current source? I think all of you know this. You'll use a PMOS transistor, correct? Okay, so we went from here, we came from here, and now so of course you'll need VB plus. Okay, this is good. Excellent. How do you add VB and VN at the input? You add a capacitor, pass the signal through that, you add a large resistor or an inductor. Okay, so you can do this. If you do this, what is the swing limitation? What is the maximum swing possible at the output? Huh? VD sat above ground and below VDD. VD sat below VDD. So let's call this M1 and M2. First of all, what is the bias voltage at this node? Huh? It is not well defined at all. Okay, so normally this is not a good way of biasing it like this if you leave it like this. Now what will happen is that it will get biased somewhere below between VDD and ground, that you do know, but it's a very ill biased circuit. Okay, this is actually, so if you just purely look at the bias point, you have an NMOS biased with VB. Okay, I'll call it VB1 and VB2. VB1 and VB2. Okay, the NMOS is biased with VB1, PMOS is biased with VB2. This is actually a very bad circuit. You are basically taking two current sources, putting them together and saying what is the midpoint voltage, right? As you know from analog circuits, this is a really bad thing to do, because you are basically allowing the drain compliance, right? So basically there will be some compliance of drain current to drain voltage. Okay, you are allowing that to set the bias point. Okay, you are designing these circuits to have a very large RDS. Channel length modulation will finally set the output bias point. Okay, and it is very possible, if you do not choose VB1, VB2 correctly, if you have large channel length modulation, you can easily push one of these two guys into triode. Bad idea. Okay, the further problem here, the more important problem here is that because you are talking about RF circuits, you are not going to unnecessarily increase the length of the device. By default, you are going to start with minimum length. Is there any reason to go higher than minimum length? Probably not. In a majority of cases, probably not. When you designed your LNAs, did you try anything other than minimum length? Probably not, right? So you would have tried it, but the question remains why you tried it. Okay, there is no strong reason to try a longer device. Okay. Now, there are some very, very extreme cases. There may be a process which has really bad flicker noise, where increasing the length gives you better noise. That is possible, but extremely rare. Okay, normally you stick to minimum length. There is absolutely no reason not to go higher. Now, in the case of the LNA, of course, let's say common source LNA, you're trying to do input matching, right? Maybe you feel that you anyway have to increase CGS. So to do that, you might increase the length anyways. You anyway have to slow down the system, okay, to get an higher value of LS. But these M1, M2 are going to be M1 definitely, M2 may not be, but M1 definitely is going to be minimum length. M2 is just a current source, that will be longer length. What is going to happen is that the RDS of M1, the channel length modulation of M1 is going to be really bad. Okay, you're not going to fix that by slowing down M1. That's a really bad thing to do. Remember, this is a device, you're trying to get power out of this. If you slow it down, right, you're reducing FT by increasing the length. Okay, the amount of GM that you get, the amount of maximum power that you get will be lower. Okay, eventually you will start compromising the ability. You are making it more inefficient. You should never do that. So this is a bad thing to do. Okay, Can you suggest some other better circuit? Use a current mirror to bias both at the same time. What do you mean, both VB1 and VB2?
Both NMOS and CMOS to have the same current.
How will you do that actually? If you connect them up like this, is it ever possible to use current mirrors to do it? See, VB1 and VB2 may be generated from current mirrors. How else will you generate, right, voltages that are well connected to M2 and M1? Probably only through current mirrors. But if you just use simple current mirrors, you can't do this. Is there a better way? Feedback. Only for bias though, not for the signal. You can make it such that feedback exists only for bias and not for the signal. How will you use feedback to bias this? Well, I'll give you a simple way to do this. So instead of setting, I'll just show the bias picture alone. So one simple way to do this. So let us say this is already set. Okay, VB2 is already set, it's a current source. Now what I have to do, I can't independently set VB1. I'll have to set VB1 such that it is a correct value for a current generated by this guy. This has some current I. I am trying to pass that through an NMOS. Okay. Now one way to do this is, so this is how my signal is coming in. For example, I could do this, a very large resistor. Okay. Can I do this? Of course I can. And because this is RF, I could also do this. I could also use a large inductor. Correct? I could do that. So of course the signal comes in like this. Okay, I could do this. All of these things will bias the output voltage to, what will the output voltage be? What is the DC value of the drain? Is VGS1. Clearly. All of these things will bias it at VGS1. But this is not the best way of doing it, right? I want to do even better. I want independent control. So imagine now I actually want to bias it at what is the optimum voltage to bias the output at? VDD by 2. I want to bias it at VDD by 2. How do I do it?
So we can take a reference VDD by 2 and
Very simple, exactly. So what I have to do is I need to use common mode feedback, okay, to set it separately. This is also feedback, okay, DC feedback, except I'm doing it through a resistor. Now I'll have to explicitly do it using an op amp. So what I'm going to do, I could do something like this, but of course now I need to break the loop for the signal. I need to do this only for DC. Okay, so I might need to add a large resistor or an inductor here. Okay, I can do this. Okay, because it's not drawing any current, I can do this. Okay, because I'm biasing the gate. Now if I do this, okay, so if I do this, VB1 will be set, okay, such that the output VODC is VREF. Okay, typically the best VREF is VDD by 2, right? You're at mid rail, you can swing above and below that. Does it make sense to everybody? Okay, any questions? Okay, of course I could also choose to set, I could set VB1 independently and feedback to VB2, right? I think that's, you're all aware of that, I hope. I don't have to show that explicitly, right? I could choose to not touch the signal. See, this one I'm operating on the signal path, right? I could decide this is not a good way, right? I could set this voltage independently using a current mirror and set VB2, right? I could also do that. Okay, can I do even better than this? You have seen all of these circuits in the analog circuits course. I think all of you have taken the analog circuits course here. Oh, I think all of you have. Okay, you have not. Okay, you will see this in the analog circuits course. Okay, can you do better? Remember the circuits that you went through in the analog circuits course. What did you do after this? Sure, you can do all of that. What happened next? What did you do next? You remember there was one more better modification of this circuit. What was that? What is the gain of this circuit at low frequencies? It is GM1 over, okay, GM1 times R01 parallel R02, correct? If you have an RL like 50 ohms, it is not that much. It is only GM times RL. 50 ohms is too small. Okay. Go back to the analog circuit. What additional modification did you can do even better than this? No. This is very good, but you can do better. Very simple. You can give the signal to the PMOS also. Remember, this was the active load that you studied first. You transition from the active load to the inverter. Do all of you remember this? Do all of you remember this? So what happens is, right now the PMOS is being used only for bias. The NMOS is being used for the signal. Correct? But you can do biasing, with both and signal with both also. Okay? So the next transition, next circuit should of course be something where okay, if you design the widths of the I think I'm not going to go into the CMOS inverter here for sure. Okay, quick recap, the only difference between the NMOS and PMOS are the threshold voltages and mu and mu p mobilities, correct? Those are the two differences. For a majority of circuits, threshold voltages will be almost the same for a majority of processes. Mu n to mu p will be anywhere from 2 to 3 times, right? Mu p will be approximately 2 to 3 times larger than mu n. Okay, so to compensate for that, you will basically try to make the PMOS about 2 to 3 times wider compared to the NMOS. If you do that, right, the strength of the PMOS, the GM of the PMOS in other words, will be the same as the GM of the NMOS. Okay. Okay, if you size them in the ratios of their mobilities, okay, what will happen is that the GMs will be approximately the same. Okay, the gain you can get from this circuit, okay, if you don't load it, the maximum gain you can get is what? Very close to the intrinsic gain. The previous circuit would have given you the intrinsic gain of the transistor times half, because you have GDS-N and GDS-P in parallel. This one will give you very close to the intrinsic gain of the transistor. Okay. In our case, you have RL. Okay. At RF, you have RL of 50 ohms. Okay. So GDS and all will typically not matter. Okay. I'll say approximately times RL. Understood? Okay. How do you bias this circuit? So one simple way of biasing it is you could do this to force the inverter to be biased at the trip point. Okay. This is not always the best. Okay. But this is something you can do. I'll just call this some RB, and then of course you have to AC couple the input. Okay, I'll just show these as infinite blocking capacitors. Okay, I think you folks know how to choose these capacitors also. Okay, but if you do this, the inverter will be Everyone is able to see this? If you look at the inverter characteristics, it looks something like this, correct? So if you do this, it will be biased midpoint of this characteristic. If you set Wp by Wn equal to mu p by mu n, etc., and approximately Vt's are the same, this will be approximately at VDD by 2, VDD by 2. Okay, if it's a completely symmetric system, the input bias voltage will be equal to the output bias voltage, which will be equal to VDD by 2. Okay, so now let us take this as a template and see what this will give. I want to get power out of this. So this is VDD, this is ground. Okay, what is the maximum swing of this circuit? VDD by 2 minus VOV. What is VOV?
Overdrive of PMOS minutes and
okay. Okay. So if you design this correctly, right? If you make sure that WP by Wn is same as mu p by mu n, and let's assume that threshold voltages are the same, right? Will they have the same overdrive voltages? Yes, they will. Of course they will. Okay, if you design it properly, they will have the same overdrive voltage. Okay, if that is the case, right, from VDD by 2, if you start swinging higher and higher, okay, you can
2 VT.
huh
2 VT.
2 VT is being,
It can go up to VDD by 2 plus VTP and
why is that?
VDD minus 2 VOV.
Why is it VDD minus 2 VOV? So what is the maximum swing at the output? That is what we are interested in, correct?
linear region is allowed.
So remember, this is the magnitude of the gain, but remember that this circuit is actually inverting. Okay, so maybe I'll explicitly show that. Okay, first of all, this is an inverting amplifier. So the first thing you have to do is take this guy. Okay, I'll apply a sinusoid and keep increasing its swing. What will the output look like? Output will look like a larger version of this. Correct? Okay. So if you keep moving along this, if you keep increasing the amplitude of the input, right? So what is clearly happening is, as the input is increasing, drain is decreasing. Okay. Of course, at some point of time, the NMOS will go into triode. Okay, that is not allowed. Okay, that is normally not allowed. It is not a linear amplifier. Okay, if the circuit has very large gain, okay, you can almost ignore the input swing. Okay, and you assume that the input is already set at VDD by 2. How much can the output swing without sending it into linear?
Plus VT minus VT.
So it will go to VDD by 2 minus VT n to VDD by 2 plus VTP. Understood? It cannot swing more than that without sending the devices into the nonlinear region. Does that make sense to everybody? If you have very large gain for this circuit, you assume that this is approximately equal to VDD by 2. Okay. The output can go only 1 VT below the gate voltage. Correct? It can swing above that as much as you want. For the NMOS, the output can go only 1 VT below the gate voltage. So the maximum swing you can have is about VT at the output. You understand? If you go any higher, it can give you more swing. Of course, you know, I can switch, right, the device such that it goes into the triode region also. But if you want linear operation, this is the maximum swing you can get. Okay. I'm assuming linear operation, which means only in saturation, no triode, no cutoff. Okay. By the way, this gives you a fairly crude, simple PA, but normally it is not the best PA. You can do better. Okay. This is a very easy PA to build because there is no extra biasing circuit, right? But really what happens is, What are the degrees of freedom you have in designing this PA? Huh? Only transistor? How many degrees of freedom? If you had to change your design, correct? I want to change this design. How many things can you change to affect your design? Of course, I mean within limits, of course, right? Don't come in and tell me I want to change RL. You cannot change RL. RL is 50 ohms right now. Okay, I cannot change RL. Okay, I'm already assuming that GMP is the same as GMN. Correct? Because I want it to be biased at VDD by 2. Right? What is that? Only width of the transistors. Okay, is the only degree of freedom under your control. There's nothing else. You set the width of NMOS, width of PMOS is already, let's say, 3 times that of the NMOS. Can you change the bias current through this device? You can't. Okay, based on the inverter characteristic, whatever bias current you get at that bias point is what you get. Understood? It is not necessarily a good, clearly it is not a good PA if you want more degrees of freedom. Okay. Sometimes if you want to, yes? Maximum, well, swing is the same as amplitude. Why swing? Okay, so okay, then if that is your this thing, then I'll just call it amplitude. Fine. Maximum amplitude is Vt. Okay. Normally, when you say swing, it can also mean amplitude if you don't say anything. If you say peak to peak swing, then it is this thing. Yeah. So maximum amplitude is Vt. Peak to peak swing is 2 Vt. Okay. This can be high enough for some applications. Suppose you have an application which is low cost, right? Low performance, low power. You can do something like this. So you could actually use, let's say you have a Bluetooth transceiver. You could build. I can conceive of somebody building a PA like this. Okay.
But the frequency of the signal, we are not considering the AC gain.
This is the AC gain. The AC gain at low frequencies is this. The AC gain at high frequencies is this.
But like the internal parameters of the
Absolutely. Okay. Now, what is that comes in the limitations of this circuit. First of all, till what frequency can this circuit operate? That's what I'm planning to do next. But anyway, since you have asked the question, let us do that. What is the limitation? If this is so great, of course, the number of degrees of freedom, right? So the limitations of the circuit clearly are, so first one, okay, so as you can see, pretty much the only thing you can set is Wn, correct? You increase Wn, automatically bias current will increase. You cannot increase or decrease them independently. More importantly, you go back to one of this circuit. In this circuit, can you set them independently? Do you have more degrees of freedom? Actually, you do. Okay, note that. Okay, I want to, let us say I don't want to change the width, I only want to increase the current. Can I do that? Of course I can. All I have to do is change VB2 or change the size of this device or both. This is a current source. I'm going to feed more current through this. I can change width independently. The bias point will get set accordingly. VB1 is not being tied to directly to the bias current. It is being set by the feedback network. You understand? I can change GM. I can change the gain of the circuit, GMN, and the bias current. So the width and the bias current can be set independently. Right? Same thing for this circuit also. Right? Same thing if you did the feedback to this. So if you had a choice, you'd probably go for this one. Of course, it requires an op amp. Number one. So you now need to design the op amp. Number two, remember that this is a feedback network. You need to make sure it's stable. You don't want that oscillating. Right? The feedback network better be stable. Normally this op amp will be a one stage op amp. Okay, the second stage is formed by this NMOS transistor. Okay, it's a two stage loop. You have to make sure it doesn't ring. The usual, I think all of you have done analog circuits, you know about this. We'll need to compensate this loop most probably. Okay. Yes. Yes.
Like you told that the vein is like this.
Yes.
And the phase is getting shifted. So, but across a resistor, phase shift should not ideally happen a voltage.
Why not? Actually, why not?
Because like resistor is not really known for changing the phase.
But it's not the resistor that's changing the phase, it's the transistor that's changing the phase. What does that mean? Actually, I don't understand.
So like,
See, this resistor will be large enough such that for AC it will be almost open circuit. It will not need not be, but it's a large biasing resistor. Right? Now you can choose it to be small also. So as he's pointing out, there is an AC current flowing through RB. That's all. That is all. There will be an AC current through RB. So what?
so the question was like, across a resistor, I'm not really seeing like suppose like we have a resistor between 2 points A and B.
Mm-hmm.
So like if we have an AC signal through a resistor, like
Hey, this one also had swing at both points. All of these circuits have. I don't understand. Any case where you use a resistor, you have the choice of either having it to ground or between signal points. In any random network, why? What is the problem in having signals across both ends? Okay, maybe you can ask me after the class. Maybe I have not understood the exact point. Okay.
So actually, I was remembering the phasor diagram which I used to draw in class 1. So there the voltage current relationship, like the resistors usually don't really shift the phase.
Correct.
So because there's only real part of the impedance.
So the current through the resistor will be in phase with the voltage across the resistor.
Yes.
That's all you can say about the resistor. The resistor, I don't know what you mean by saying resistor shifts or does not shift the phase.
Yes, so that's what
Even in this case, that's true, man. Even in this case, that's true. Okay, the resistor, what I'm trying to say is the resistor is not doing any shifting. Okay, it is the rest of the circuits that's doing the phase shifting. Okay, I'll discuss it with you. I think maybe you have misunderstood what the resistor does. Okay, I'll discuss it with you after during the break. Okay, any other questions? Yes.
In reality, while running the simulation, you can't make the VTP same as VT.
Okay.
So in that case, it should be VDD minus the minimum value of VTP. That should be the considered.
Of course, absolutely. That is right. If VTP was not equal to VTN, right, the minimum of VTP and VTN will be the maximum swing, the maximum amplitude that you can have at the output. Absolutely. Neither of the transistors should go into triode or cutoff. Okay. So the other limitation is bandwidth. What is the bandwidth of the circuit? Yeah. So what will happen? Remember that this circuit has some additional parasitic capacitance. Okay. So effectively, you have an RC bandwidth. The transistor acts as a transconductor, right? So the signal current flowing out splits between the load resistance and the capacitance. The capacitance is the drain bulk, typically the drain bulk capacitance of your own transistor. Okay. So clearly there is an RC bandwidth for this circuit. If you go beyond a few gigahertz, it's harder and harder to make this circuit work. Does it make sense? Okay. Instead of saying, I'll say parasitic capacitance at output node. Okay. Typically it's CdB. Okay, maybe 2 or 3 gigahertz in 65, 45, etc. Okay, what else? Any other limitations that you can think of? So that is the RF limitation you are asking about, Akash. The high frequency limitation that you are asking about is primarily, if you just plot the bandwidth of the circuit, it's almost simply an RC bandwidth. Okay. Okay. What else? Any other limitations that you folks can think of? What is the maximum swing? So what is the maximum output power? Right? The maximum out. Okay. What is the maximum output power?
4 VT square.
Why 4 VT square? So I have a resistor.
4 VT square by
Across this,
8.
I have 0 bias and I have a swing of VT. Correct? Huh?
VT by 2 R.
VT by 2, VT by RL is the current. So even dimensionally it's wrong what you are saying.
So VT square by 2 R.
VT square by 2 RL. Why is it VT square by 2 RL?
VT is the T.
Okay.
VT square RMS is VT by 2.
Okay. So if you have a sinusoid of peak value VT, the RMS value is VT by root 2. Okay. VRMS squared over R gives you the power. Okay. So the maximum output power you can get. So VT squared by 2 RL. Okay. In fact, VT squared by 100. Literally. Okay. For example, let us say VT was half a volt. I'm just giving you an example. What is the VT of the process that you are using? What is VTN and what is VTP? It's about 400, 500 millivolts. Let's take example of 500. That is typical for most modern processes. What is P out max?
2.5
2.5 milliwatts. Does it make sense? Okay. So beyond this is the maximum linear power. Beyond this, it will start to compress. Okay, it will compress fairly slowly. By the way, this thing doesn't. The good thing about this circuit is that it doesn't immediately like kind of stop, right? It will compress slowly. You can get a little bit, maybe if this is 2.5 milliwatts, probably the saturated power. What is the saturated power? Let us say I, drive the circuit with higher and higher amplitudes, right? What is the absolute maximum swing I can get out of this? What VDD by 2? Why? VDD by 2?
VDD.
What is VDD?
Sorry. Okay, the amplitude is 80.
Maximum amplitude is VDD by 2, correct? So saturated power, I'll call it Psat. Okay. All of you know what Psat is? Saturated power. Okay. You may know this, but I'll define it anyways again, just to be sure. If I were to plot P out versus P in let us say dB, what will the curve look like? So first of all, what will be it will be a straight line for very low powers. What will be the slope of this? 1. What is the y-intercept? Gain in dB. Okay. And eventually what will happen is it will start compressing. Okay. And I think all of you already know about the 1 dB compression point. Okay. And if you drive it even beyond the 1 dB compression point, a few dB later, it will really give you, so let us say 1 dB happens here. This is the input P1 dB. This is the output P1 dB. Okay, the same thing. Now, okay, I'm going to drive it even harder. What will happen is that it will saturate at some power. So that will again be 1 or 2 dB above the. Okay, this is very badly drawn, but Let me see if I can draw it better. I'll draw it like this. Okay, that is PSAT. Of course, PSAT is always at the output. There is no concept of PSAT at the input, right? You can keep increasing input power, output will just be PSAT. Okay. What is PSAT for this amplifier? So this is of course VO max by 2 RL, VO max squared. Okay. What is VO max? The peak amplitude, VDB by 2. Okay. Any questions? What is in your case? What is VDD? 1.8 volts. Okay. What is PSAT? So 0.9 squared by 100. Okay. So 0.81, 0.0081. So 8 milliwatt, 8.1 milliwatts. How much is that in dB? In dBm? Huh? Roughly 9 dBm. Okay. 10 milliwatts is 10 dBm, right? Around 9 dBm. Okay. Okay. Remember, a lot of these numbers are quoted in dBm instead of milliwatts. Okay. Okay. Any questions so far? Yes.
So, like, if we give a sinusoidal input, the output won't be sinusoidal.
Yeah, it won't be sinusoidal. It will be square.
If it's a square wave, then there should be a factor of 4.5.
Yes, there could be. If you drive it really hard such that it becomes a square wave. Normally what will happen is that the RC bandwidth will never allow you to get a square wave at the output. Okay. Normally the RC bandwidth will never allow you to get a square wave. You'll never get anywhere close to that. Okay. Second thing is, what you're saying is correct. So normally you will have to put in a filter, okay, to remove all those additional harmonics also. All those things I'm not showing, but you're right. Okay, you're absolutely right. Any other questions? Okay. Now I want to do even better. Clearly this is, I have, like, you know, the circuit has like 2 or 3 limitations which are very hard to get out of. Okay, let us see if we can squeeze out a little bit more. Can you squeeze out anything more from the circuit? I want to, let us say, see, there are amplifiers where you don't necessarily have to operate in linear mode. Okay, there are amplifiers where, for example, imagine your modulation is some kind of frequency or phase modulation, FM or PM. There is no information contained in the amplitude of the signal. If that is the case, okay, you can very well operate in this region, no problem at all. You understand? Because this is needed when the amplifier is linear. Okay, whereas what I am telling you is the information is carried in the zero crossings. If that is the case, this doesn't matter so much. Okay, but I still want to improve this. So the clearly the linearity is less of a problem. This max P out is less of a problem. PSAT, I want to improve this further. Okay, how can you do this? Okay, let us go back to P out. I want to increase P out itself. Right, PSAT is unnecessary selling into the nonlinear region. So let us discuss with P out itself. I want to increase this output power for this circuit. Can you tell me one simple way to do that? What is the output power, maximum output power from this circuit? It is VT squared over 2RL. Okay, can you change the VT of the device? You cannot. Can you change RL? You can't, because it's 50 ohms. However, what you can change is the effective resistance seen by the PA. You cannot change the final RL. You cannot change 50 ohms. What you can change is the impedance seen by the PA. Okay, so what you need to, the next stage of this circuit, okay, the next stage of any PA circuit for that matter, Okay, you're putting in some power. Now you can put an impedance matching network for IMN. Okay, such that RL is different from 50 ohms. If I want more power, what kind of RL should I be choosing? Much smaller, correct? So you can see that the power linearly changes with RL, correct? If I make RL 1/4, I'll get 4 times the power. I got 2.5 milliwatts, okay, with 50 ohms. If I make it 12.5 ohms, okay, I will get like 10 milliwatts. Okay, that's about 6 dB higher. That's quite a bit. Okay, so I can use an impedance matching network. Now again, this takes care of your filtering problem also. You anyway don't want to put out harmonics, even if you're operating in the nonlinear region. You can design this matching network such that it's a narrow band match. You can design, it can be an L match or a pi match, etc. Okay, the L match does not give you a degree of control over Q. The pi match does. You anyway need a blocking capacitor. Remember, you need a blocking capacitor at the output. Okay, if you don't want to put out a separate blocking capacitor, you can choose a matching network which has a series capacitance. All these things are all ways of optimizing the circuit to do better, right? I'm not going to discuss that separately, right? That can all be done. I can include 2 functions in one, things like that. But fundamentally, I can put a matching network, right? I need a downward matching network from 50 ohms down to something. Okay, I want to keep increasing the power. Can I just randomly keep decreasing, RL? Let us say RL is the input impedance at the input of the matching network. So I am taking 50 down to some RL. Can I keep randomly decreasing RL?
You're limited by the quality factor of the matching circuit.
Correct. So eventually you will be limited by the quality factor of the matching network. Okay. So imagine that you're going down from 50 to 1 ohm, right? If the series, let's say you have an inductor in series in the matching network, that will automatically take it to 2 ohms. Okay. Automatically your this thing, you'll be losing half the power in that 1 ohm resistor in the inductor. You understand? So you can't arbitrarily reduce RL. Okay, so one thing is Q of matching network. Anything else matters? Of course, other things, more practical things. If I'm going to lay out the circuit, I need to make connections with wires. The resistance of the wires may be 1 ohm. I need to worry about that, right? So layout parasitics. Will dominate a lot more.
So if we are arbitrarily decreasing RL, we might even increase the area of the matching network.
Of course, that is definitely a concern. Correct. Okay, so the area of the the value of the components, these are all concerns. Okay, but I can do this, so I can do even better. Clearly, right? That is a practical limitation. Okay, now we have reached the limit of the circuit. Okay, like I told you, you can put out a few milliwatts, right? Something like Bluetooth or something. You can use this kind of PA. I want to do better. So any other suggestions? Let's go back. Now we go back all the way to the beginning. We started off with the common source amplifier, right? We said common source, you need a biasing, you need the current source. Okay, we did this. Now I'm going to branch off from here. From this point, I want to add a second branch. Do you know any other ways of implementing current sources? Huh? You can use an infinite inductor, just like an infinite capacitor is a voltage source, an infinite inductor is a current source. Okay, remember that. Okay, if I take an infinite inductor with a current I through it, this is identical to a current source with value I, because at any AC frequency the infinite inductor gives you an open circuit. Okay, the current cannot change through the inductor. Excellent. So now this is going to be my circuit. So signal and DC applied at the input, that stays the same, that has not changed. Okay, what will be the bias current through the circuit? What will be the bias current through the circuit? Huh? The current corresponding to VGS of the transistor, which is VB. Okay, so this will be biased at some current. That current will of course flow only through the inductor. Okay, excellent. What is the output bias voltage? Is VDD. Excellent. So one difference from the previous circuit is that the output bias voltage is at VDD. Okay, what is the maximum swing of this circuit? So depends on VB. Okay, it is VB minus VT, and what is that? That is the VD sat of M1. Okay, so if you start swinging, is there any swing limitation on the upper side? There is absolutely no swing limitation on the upper side. It's only on the lower side where you have the transistor. Okay, so the maximum swing is, the maximum amplitude is VDD minus VD sat of M1. Is that okay? Any questions? This is the maximum swing of the circuit. On the upper side there is no limitation, so the lower side limitation will fix the, if you do this till this point, the circuit will be almost linear. Okay, is this larger or smaller than the previous circuit? Of course it's much larger. Okay, VD sat is under your control. VD sat depends on I and W, width of the NMOS transistor. Okay, you know that VD sat you can make it a couple of 100 millivolts easily. Okay, VDD is 1.8 volts. Okay, so you can imagine that, so minus, let us say, you can get an amplitude of 1.6 volts. How much did you have earlier? About 0.4 volts. You have about 4 times the amplitude, correct? So how much power will you get? 16 times more power. Okay, what is 16 into 2.5? 40, right? So you'll get about 40 milliwatts out of this, just blindly. Okay, you can see it's about an order of magnitude higher linearly. Okay, so $40 milliwatts. Okay, what is PSAT? It will be slightly higher because now VD sat you can now push it into the linear region. So PSAT may be like a dB or 2 higher, not much more. The difference between P1 dB and PSAT will be very large in the case of the inverter. Okay, because VT is the swing, but maximum is VDD by 2. There's an order, one of them is 0.4, the other is 0.9 or 1. So there will be like 6 dB difference. In this case, there won't be, there will be much smaller. So it is linear to a larger dynamic range. But PSAT is also higher. Fundamentally, this circuit allows you larger swing, primarily because you have removed the limitation on one side. And more importantly, you are biasing the output at VDD. Okay, so that gives you an extra VDD by 2 swing that you did not have. Okay, so fundamentally this circuit is just better. You don't have the parasitics from the PMOS transistor. You only have the parasitics from the NMOS transistor. What is the bandwidth of this circuit? It's also going to be wider. You understand? So the pluses for this circuit: wider bandwidth, larger swing and P out. Okay, any other pluses? Of course it has slightly lesser gain, but that's okay, right? You live with that. It has so many other positives that this thing is not a big problem at all. Okay.
we are going to stick with RL, we can directly use the inductor image. We can, if we are not using a matching network, we can directly match the output with the help of the.
Yes, you can. Actually, I'm going to come to that next. But before I do that, I was actually coming to that next. But before I do that, I had one more, I guess, a couple of more points to cover. Okay. First of all, I could have, if I could pass DC current through RL, I could have just chosen to put RL instead of the infinite inductor. I could have put RL here. I could have branched off. I didn't show that branch separately, but instead of doing this, I could have pushed RL here. Correct? If I could pass DC current, that will of course have the same limitations as the other circuits. It will be biased at VDD by 2, right? On the lower side, you will still have a swing limit, right? It will still not be as good. You will still have an RC bandwidth. It doesn't help with any of those. In case, I just wanted to point that out in case any of you have questions whether that could be done. Okay. Now, before we go on to the matching, there is actually one more point I wanted to discuss specifically about this circuit. Okay. We have been considering the point where the transistor goes into triode. Correct? Is there any chance that the transistor could go into cutoff for this circuit? Yes, depends on the input swing. Actually, what it depends on is not just the input swing. It depends on the input bias voltage and the input swing. Correct? Because we have been assuming that the circuit has a lot of gain. Therefore, it is, you can ignore the input swing. But that automatically assumes that the transistor never cuts off. That need not always be the case. We'll return back to this a little bit later. Okay, you will find out how all of them tie back in together when you do the calculations for a sample circuit. Okay. Now, but I want you to keep that in mind. Okay, this circuit could potentially cut off. Okay, if the when will it cut off?
When the bias current and the incremental current
becomes equal, or you can alternatively put a condition at the gate saying that the absolute input voltage at the gate of M1 falls below VT. Either of these two conditions are allowed. Okay, they are almost the same but not exactly the same. Okay, because of the square law of the device. But for all practical purposes, we can assume you choose one and calculate it. Okay. You will find that you will have to put that. Make sure. Okay. When we do the calculations, we will discuss that. Now, if I want to get even more power out of this, I don't want 40 milliwatts, I want 100 milliwatts, right? Of course, I could take this circuit, put a matching network. Okay. Hey, did I say? Yeah. Impedance matching network, the matching network. I could do this. Okay, I can make, this is RL, that is our definition. This is 50 ohms. I could do this. I could match RL 50 ohms down to RL, maybe let's say 25 ohms, 12.5 ohms. Okay. If I match 50 ohms down to let's say 12.5 ohms, how much power will you get? More? You will get 4 times the power. Instead of 40 milliwatts, I can get 160 milliwatts. Right? Okay. I can get 4 times the power. Okay, these are all standard ways you can try to put stuff together to do it. Now, of course, this matching network will also be an L match or a T match or a pi match, right? You can the matching network, as before, will make the circuit fundamentally narrow band. The circuit itself is wideband. Both the inverter circuit and this circuit are wideband circuits. I hope you realize that. Okay, if you really take an infinite inductor and build the circuit, right? It'll act as a current source. Signal current will flow into RL, right, all the way down from extremely low frequencies all the way up to some RF frequencies. The primary limitation is in the drain bulk capacitance of the transistor. The same thing will happen. There is an RC bandwidth again in this case. Okay, you could again have CDB playing spoil sport for your gain. Okay, because at the end of the day, current splits between these two. Now, one point I didn't mention earlier, but I'll anyway mention now. Okay, note that this circuit can be improved further in a couple of ways. First of all, CDB can be absorbed into the matching network. That will give you even better bandwidth. That will give you the bandwidth of the matching network itself. You understand? There is some current being stolen into CDB at any frequency, right? You can improve the circuit by building the matching network to push that current into CDB so that signal current will flow into the load. So you basically match the input of the matching network, RL plus JX. Okay, in fact I'll show it explicitly. It is RL plus JX, but maybe I'll show Y, because we are talking about, yeah, no, it's okay. Yeah, exactly. Okay, so the admittance, so the susceptance portion, okay, will cancel out the drain bulk capacitance. It should be inductive in nature so that you absorb the capacitance. Okay, this will take care of the signal current. Signal current will no longer, you will not be stealing signal current from the transistor into CDB. You could do this. As Lakshman pointed out, you can absorb this infinite inductance into the matching network in specific cases. For example, what kind of, let us take the case of a pi match. Okay, let us say I'm going to build the pi match like this. So I'm going to try to optimize this circuit by removing components. So remember that I needed an infinite capacitance here. Okay, I want to get all these functionalities together. So what I'm going to do, I'm going to choose this is my matching network. Okay, now there are a couple of problems. So, but let us do the easy stuff first. This is the infinite cap, correct? And this is also to, this is what is outside the matching network. Okay, I don't need two capacitors in series. The minute I have one capacitor in series, I don't need the second infinite capacitor. So the first thing I can do is get rid of this guy. I don't need this anymore. Anyway, the inductance is going to ground. Okay, I'll let C itself perform the job of DC blocking. I don't need a second very large DC blocking capacitor. That will definitely save area. Okay, what else can I do? There is one problem though. Remember the circuit, this bias point is at VDD. Okay, this bias point is at ground. So I want to do this, but this is a bad idea. Correct? I don't want to do this. The better thing to do, of course, is to what? I don't want to do that. I don't want to add a DC blocking cap. This is at 0. This is at VDD. If I just connect the matching network like that, the DC bias values are different. I cannot connect it like that. What should you do? I can add a DC blocking cap there, but I don't want to do that. There is an even simpler solution. I of course connect this to VDD. It's after all signal ground that you need at the bottom of the matching network. Okay, a VDD is a signal ground also. Okay, now the minute you do this, note that I have both L1 and infinite inductance in parallel. Okay, looks like I don't need this, isn't it? I basically have, that's what Lakshman was saying, right? So you have an infinite inductance and the inductance of the matching network in parallel, right? Which will what is the equivalent of L1 and infinity in parallel to inductances? It is just L1. Okay, so if you are to build this circuit, I'll show the circuit for this specific case. There may be other matching networks where you can't do this so easily. Okay, so the matching network can be naturally integrated into this fairly straightforward manner. Okay. Again, going from an infinite inductor to a smaller inductor is very easy. Okay. I want to absorb CdB, that can also be done. The value of L1, C and L2 will change. I can absorb. I'll just redesign it for that new matching network. Any questions? So this is another advantage of doing this. But you do all of this, clearly it's going to become a narrowband circuit. It is not a broadband circuit anymore. The minute you integrate the matching network into your biasing of the circuit, it becomes a narrowband circuit, not a broadband circuit. Okay? If you have a narrowband application, you need a narrowband PA. If you have a broadband application, you need a broadband PA, of course.
But most of the RSSs are narrowband.
I want to use the same PA for 2 bands. Why should I have a separate PA for every band? If a single PA can do the job, why should I keep designing one PA for every band? If I could just do let us say I had a low pass PA which works from all the way from DC to 5 gigahertz, right? Why would I want to design like one separate PA for everything when one design will do? Okay, let's stop here. My throat is starting to give out. We'll take a short 10-minute break and then we'll come back and start. Okay.